Let's begin the 569 discussion on Tuesday, October 15th, 2013.
Okay. Okay. Good evening, everyone. Welcome to the 7th discussion. Can everyone hear me? Can you guys hear me at the back? Okay. Welcome to the discussion 7. Today I'll be basically give you some announcements like similar to last time, and I'll give some hints for the homework 3 problems. Then I'll also discuss some, if time permits, I'll discuss some sample problems from previous midterm exams. For the announcements, yeah, this is same as last time, so please watch out for emails and announcements from TAs. I think some students missed a couple of announcements, mainly because either your email box inbox is full, and you might be missing out the emails from TAs, or yeah, so basically the email is not being delivered to some students. So sometimes it bounces to my inbox, so just make sure your inbox is not full. And also please regularly check discussion board. There will be some very good threads on the discussion board where students would have posted similar question, similar to your doubts. Then again, please start your homework early, and so that you have enough time to finish it before the deadline. Again, I'm just repeating the same thing from last time. So submit your homeworks at least 1 hour before the deadline. I think homework to submission was pretty good. I think almost everyone submitted on time, except a couple of students. So it's pretty good. And the late homework policy is similar to what was explained in the homework 1, lecture 1. Yeah, if you have any questions, feel free to stop me and ask any questions. This is same as last time. So if you cannot finish everything on time, submit whatever you have, and the late homework grading will be decided by Professor Ko. So homework 3 is due on 3rd November, so you have around 19 days from today, I guess. 19 or 20, yeah. These dates are decided by Professor, so you need to... Yeah, midterm will be after the 3rd, I guess. So, it's announced already? Okay, then I need to talk to Professor. I think, so was it was announced by whom? In the schedule? Okay, then we'll talk to Professor and let you know. So, I guess in that case, maybe it will be extended, or the midterm will be in the next week, not on November 1st, maybe November 8th. Yeah, so you'll have some time to prepare for midterm also, so don't worry about that. Yeah, thanks for that question, actually. Any other questions? Homework 3. Actually, homework 3 is much easier than homework 2, so I guess you can finish in 2 weeks. I don't think you need 3 weeks for this. Anyway, I'll give you some hints. Yeah, so homework 2 grades will be out this week. So grading officers will be announced later this week. Yeah, homework 3 hints. So before talking about homework 3, I'll discuss an algorithm which will be useful for the previous, the future homeworks as well as the previous homework. So this is called as connected component labeling. I think some of you already know this algorithm and use it in the homework too. So this discussion, basically I'll explain this algorithm for the other students. So connected component labeling is algorithm where basically you can find all the connected objects in the given image and then basically use use this algorithm to find all the connected objects in the given image. This is a very powerful tool, not just in image processing and computer vision, it's also used in several other fields. So it may be also useful for you in other courses like advanced DSP course, and you might need it for future homework. So the main idea is given an image, so assume it's a binary image, you can convert into a binary image. So you basically need to find out how many connected objects are there. What I mean by connected objects is if there's a pixel, that pixel is basically connected to all its neighbors. Not all its neighbors, it's like some neighbors around it. So in this example, basically this is one connected object and this is one connected object. There's no discontinuity within the same object. So that's the meaning of connected object. Is it clear? Yeah. Yeah, that I'll discuss. So in this case, it depends on the pixel. So here, what I mean by connected object is one pixel is connected to its neighbor. So this is an example. It's like these two are not connected, right? Because there's a lot of gap. So here in this example, this black is the object and this white is the background. So this is actually a very simple algorithm. First, I'll give an overview of the algorithm, and I'll discuss in detail with an example. So this is actually a two-pass algorithm. In the first pass, basically you're assigning some labels to the pixels, foreground object pixels, and you're recording equivalences of the labels. So I'll discuss what this means. And in the second pass of the algorithm, basically you're reassigning the labels, the temporary labels assigned in the first pass to the label of its equivalence class. And at the end of this, basically we'll have all the connected objects having a unique label. So each connected object will have a unique label. So in this case, these two objects will have like two labels. So yeah, the idea is basically to find connected objects, you basically try to understand the connectivity of the pixel with respect to its neighbors. So this is an example. So this is an example for four connected objects, four connectivity. So in this case, this is the center pixel. So when you're checking for four connectedness, so basically you need to check the neighboring pixels, not the diagonal pixels, not the diagonal neighbors, but just the neighbors with respect to its sides. So this is an example. So in this case, you have like four neighbors. And for the 8 connectivity, basically you have 8 neighbors surrounding the center pixel. So for this algorithm, you need not check for all the neighbors. You can just check for a few of them. So for 4 connectedness, you can just check for these 2 neighbors. And for the 8 connectedness, you can just check for these 4 neighbors. Why we do this is basically it depends on how you scan the image. So if you're doing a raster scanning, basically if you're going from left to right, and this order of checking is enough. You don't have to check for all the pixels. So this is an example. So in this, you have two connected objects because this is connected diagonally, and these are all connected. So these 2 objects are not connected. So in this example, I'll be basically denoting all the foreground objects by white and the background objects by black, zeros and ones. So this is the binary image. And we basically have to get the labels like this. So this is the initial label. This is all ones and this is zeros. Basically, we need to get a label 1, this is a label 2, and this is a label 0. So this is how actually, I'll explain the algorithm. So this is the intermediate step, like what the labels are after the first step. So if you just like scan from left to right, using the first step, basically you'll be assigning labels to each of the foreground pixels. So in this example, basically in the first pass of the algorithm, you'll be assigning labels 1, 2 for this connected object, and 3, 4, 5, 6, 7 for this connected objects. So these labels are assigned through the algorithm. So I'll go through this step by step. So in the first step, while recording these labels, you also create a table called as label equivalence class, a label equivalence table. So which basically records which labels are similar to each other. So this label equivalence corresponds to the connectivity of the pixels in the image. For this example, 1 and 2 are all connected in the same object, so they are equivalent in this table. So in the first pass of the algorithm, you will be creating these two things, this table, as well as marking the pixel with corresponding labels. And in the second stage, second pass of the algorithm, you are basically replacing all these equivalent labels with the lowest label, the minimum label for that equivalent class. So in this case, in this object, the minimum label is 1, so you'll be replacing it with 1. And in this connected object, the minimum label is 3, so you will replace the entire object with 3. So this is the final result. So now I'll go into the details of the algorithm. So just to make it much more clearer for you guys. If you have any doubt, just stop me and ask me, okay? Yeah. So this is the first pass. So here we are doing raster scanning. That is, we are scanning from left to right. So basically we scan through each element by column first and then by row. That is left to right and then go row-wise. And if the pixel is not the background, then basically you check the neighborhood pixels, which are non-background pixels, and basically if there is no such non-background pixels present, then basically you assign a unique label to that pixel. And otherwise you find the neighbor with the smallest label and assign that label to the current pixel. And you update your table, the label equivalence class, with the label you have assigned to the pixel. And in the second pass of the algorithm, basically you iterate through each of the element to the entire image again, which have been already labeled. And you just relabel the element with the lowest equivalent class. So if the label is, say, 1 and 2, you just replace it with 1. So now I'll show this step by step. Can you guys see the entire thing? Okay. So this is at the beginning. So given this image, basically no labels are assigned to the objects, and the label equivalence table is empty. That is, this table is empty. So you start scanning from this corner, so left to right, raster scanning. So when you hit the first element, so essentially all its neighbors are all background pixels, which are all zeros. So essentially you assign a unique label to this according to the algorithm, and then you move on to and update this table. Then you move to the next pixel. So for this, you can see that this neighbor has already been assigned a label as 1. It has a non-background as a neighbor, and this label is 1. So you assign this pixel value as 1. And you don't have to update the table because the label has already been, it's already present in the table. So you repeat this. So you come to this connected connected pixels. So here again, all the pixels are 0. And since you don't know the labels for the other neighbors, basically you assign this unique label, which is 2. And you update the table, the label equivalence table. So you repeat this for the entire image. So when you come to the next row, basically for this, you can see you can observe the labels. So you have the neighbors with labels as 1 and 2, and some background pixel which are neighbors. So for this case, according to the algorithm, so go back to the algorithm. So if you find the neighbor, then you need to assign the neighbor the smallest label value. So for this example, just coming back to this. So for this case, which label should you assign? Yeah. So it's simple algorithm, right? So you just assign 1. And one important thing you need to note is you need to update the table, because in this case you found that this has 2 neighbors with 2 unique labels. So you need to update the equivalence of the table. So the label equivalence table you need to update. Basically you need to say 1 and 2 are equivalent in this for this image. And similarly you repeat this to the entire image. And this is the first pass of the algorithm. So you get 7 labels. Because for these cases, since they don't have any neighbors, you basically get additional labels, like you have 7 labels. And also you have updated the label equivalence class. And in the second pass of the algorithm, basically you're scanning to the entire image again and replacing the label with the minimum label from the equivalent class, so from the table. So for this case, the minimum label is for this object is actually 1. So that is the equivalence of 2 and 1 is 1, right? I mean the minimum of the labels. So essentially you replace all the 2's in this object with 1's. And similarly for in this object you replace all the labels greater than 3 with 3 because that's the minimum. So essentially you'll be replacing with 1's and 3's, and you have basically you obtained this result. This is the final result obtained, the final output. So you have obtained 2 labels. I mean you found 2 labels, connected objects with 2 labels, and this is your final result. So it's just a 2-pass algorithm, and basically you can find all the connected objects using this algorithm. And this is the pseudocode for this. So did you guys understand, or did I go through very fast? Go through this very fast. Do you have any questions? I mean, scanning means you're basically replacing, right? That's all. You're just replacing the labels for the image. Yeah. Any other questions? It's actually quite simple, but it's very, very useful algorithm actually. Yeah, if you knew this algorithm, the homework 2 would have been much easier, right? Anyway, I think you'll use this algorithm. Maybe you can use this algorithm in the future homework. So just know this algorithm. It will be very useful. Any questions? Okay, then I'll continue. So this code was basically borrowed from Wikipedia. So this slide was prepared by the last year's TA. I'm just reusing them. Okay, now coming to homework 3. So I want to motivate this by showing some videos for all the 3 problems. Then I'll discuss, I think I'll discuss problem 1 and 3. And if time permits, I'll discuss some sample exam problems. I think Professor has only covered this part in the class. So I'll also talk about this, which will be what he'll be covering this week, I guess. And this problem too will be covered by one of the other TAs. So, yeah, so let's watch some videos now. Okay. Just click on this. Okay, so this is actually a music video. I need to, I'll skip the ad. So I wanted to show this video because they use some simple image manipulation techniques to use it in this music video. So I'll just show you like 15 or 20 seconds.
You wish if you had one chance, so airplane, sorry I'm late. I'm on my way, so don't close that gate. If I don't make that, then I switch my flight and I'll be right back at it by the end of the night.
You can see
Right now.
Yeah, so you can see it's very useful for entertainment industries. Going back to this, this is actually a simple, another example. So here actually one of the students has used image warping to basically do some warping of the emotions for the human face. So this is actually a small video, so you can just watch it. So you can see by modifying different aspects in the image, you can create different types of emotion in a still image. You'll be doing something like this for homework 4, which will be a little bit more challenging, I guess. So if you know the spatial warping technique, you can do all this, play around with the images. So by adjusting 6 parameters, basically you can create your own emotions for your own image. You don't have to, you just need to have some parameters. Okay. So that is for geometric modification and spatial warping. So it's a very useful technique, very powerful technique. So you can use it to basically create your own types of special effects in videos or for the images. For perspective transform, I'll show 2 more videos. This is actually okay, let me show you the video and I'll explain something about the video. So this is actually an artist creation. So he's basically projecting 3D objects on a 2D space. So you'll see a lot of things happening in this video. I'll show you a part of the video. So this is the 2D screen actually. It's like a screen, right? It's very creative, but some image processing is also happening here. So just watch for like few seconds. Maybe I just... So it's the same screen, but you can see the 3D objects being created on the 2D space. I won't show you the entire video, unfortunately. But it's an interesting video. If you're interested, you can watch it later. And this video, yeah, so this is actually very useful in augmented reality, projection of 3D objects on 2D spaces. So in this example, basically, given this surface, you're projecting like 3D objects on that, or 3D scenes on that 2D space. So this is very useful. This is an augmented reality example actually. So by basically understanding the coordinates of the space, you can actually modify and design games. So this is one example. So this is for like basically projection and understanding the geometry of the images and trying to like project or design methods to basically project 2D images on 3D objects or 3D objects on 2D spaces or 2D plane. So this is an example. And for the texture classification, I'll show you a very realistic example. So this is for the railway track. You're basically you're going on the train. You're going basically you want to identify the textures of your surrounding your railway line actually. Yeah. So basically it will be useful for a lot of things. But this is an example to show like when this object when these boxes become blue, then basically it shows that it has identified some particular texture which is present in the database. So this is an example. So yeah, so this is a short video, but so texture classification and segmentation is pretty useful. Do you have any questions regarding videos? If you're interested, you can watch. I'll upload not the videos, but the links. Okay, now come back to the homework problems. Let's come back to homework problems. So For the first problem, you're supposed to do the spatial warping. So I showed you an example for not spatial warping, but for geometric modification. That is the music video, where basically you can modify the dimensions of the image so that you can project on any type of surface, or you can modify the image or manipulate the image to your desired shape and size. And you need to modify the pixel intensities also. So this problem basically asks you three parts. The first problem has 3 parts. So first one is basically you need to convert this image into this image. That is, you're doing a spatial warping from the original image to the diamond shaped image. And the second one is to the pentagon shaped image. The third one is a little bit challenging. So you're warping this image to this circular image. So let me explain, give you some hints on how to go about solving that problem. So I'll give an example with respect to another image. This is from previous year homework problem, I guess. Yeah, so given this image, this is a Lighthouse image. Forget this ABCD. Given this image, basically you need to generate this kind of image. So how do you do this? So this is the problem of spatial warping. So the main idea is, here we basically transform the coordinates or the pixel values from the original image to the output image or the desired image. So the key idea is you're trying to map the pixel values from the coordinates in this Cartesian coordinates in this image, or the image coordinates in this input image, and mapping it to the image coordinates of the output image. So we do this by actually simple triangle warping. So in this example, you can just do a triangle warping. That is, you basically take the triangles ABCD and warp each of the triangles to their respective shapes in the output image. So in this example, basically we are trying to warp this image to this. So there's some rotation as well. I mean, you're basically rotating this triangle, and basically this is the triangle this is the shape you want to obtain from this region of the image. So you can do this spatial warping by several techniques, but the one which we teach in this class is on the polynomial spatial warping technique. So for this example, since this is a curved section of the image, so you would need two second order polynomial to represent this curved region of the image. So this looks like a circle, right? Circle, the part of a circle. So you basically need a second order polynomial to capture the curvedness or the curvature or the contour of this region of the image. So what you do is, I think Professor has already covered the spatial warping. I'll go through this again. So given this triangle image, basically you want to map this image to this image. So what you do is, in the first step, you basically find the control points. Control points are the points around which you're trying to do the warping. So in this example, we are showing you 8 control points for this for the A triangle. So we have 1, 2, 3. We have 3 plus 2. So we have 8 points. These 8 points are basically mapped to these 8 points here. So in this case, this point basically maps to this midpoint. These 2 corners are mapped to these corners. And the midpoints along this line on the triangle side is mapped to these 2 lines. So basically we are trying to first map the control points and then basically do the spatial warping. So this is the polynomial or the spatial warping for the second order polynomial equation. So given this input, and this is the degrees of the second order polynomial, these are the coefficients. So we're interested in, given this input, we are trying to basically map given this input, we are trying to map the output by using this transformation, or this spatial warping, or the polynomial transformation. So the main idea is to find these coefficients, the A's and the B's. So for this example, if you can think clearly, so do you think you can warp from the the input image to the output image, can you do the warping correctly? What I mean by warping is, so this warping is basically for, transformation is basically for
time is
the
17
image
o'clock.
coordinates. So for this example, so assume you have a pixel here. This is the coordinate of the one of the pixels, which are all integer coordinates, so or fractional coordinates if you consider the image plane. So you want to map this to this region. So how do you go about doing it? So this is called as forward mapping. That's mapping from this input image to the output image. This is called as forward mapping. Do you think there is any problem in the forward matching procedure for this kind of warping? Pardon? Exactly, that's right. So if you do the forward mapping, basically you have pixels here, and some pixels may be mapped to the non-integer pixels in the output image. So what it means is you can have some pixels in the output image which don't have any pixel values. So to overcome this, and there's one more problem. So this can result in, to avoid this, you can actually do some simple techniques like round off to the nearest integer and assign the pixel value to the nearest integer. But there are some problem arises, like some pixel might get unfilled, and also there might be some artifacts in the image, in the output image. So to avoid this, basically we do the reverse mapping. That is, we take the coordinates from the output image and map it back to the input image. And the same problem arises. So if you have a input coordinate, I mean, when I say input coordinates, the coordinates of the output image, when you map back to the input image coordinates, so again you encounter the same problem. It can be of non-integer value. So to get the value from the non-integer pixels, you do the bilinear or some kind of interpolation, cubic interpolation or bilinear interpolation to get the pixel intensity value, and basically assign that value to the integer location in the output image. That's the main idea of reverse mapping. So for this equation, essentially this output coordinates corresponds to this input image coordinates. And these x and y corresponds to the integer coordinates of the output image. And the main idea is to find these values, the a and the b, the coefficients of this polynomial warping. So in this example, you need to find 12 coefficients. So you need at least 6 control points for this example. So this is a second order polynomial, so we need at least 6 control points. So in the given example, so I have used 8 coordinates, so it will be an overdetermined system. So you can solve this by least mean square approach, basically minimizing the error, the least mean square error. So if you have, in general, if you have n points, so we write the equations like this. Basically, we have a matrix which has n by, say for this example, n by 6. So the matrix size is n by 6. So for this problem, essentially, so, okay, let me tell you. Okay, the input for this system will be your coordinates of the output image, and the transformation coordinates of the mappings from the input image, and the output is essentially you need to find this a and b. So that is this coordinate. So you can rewrite this as a matrix equation, right? You have u and v on one side. You have a matrix, a matrix on, you can represent this as the matrix A, and this is your X. So basically you can rewrite in matrix formulation, and you get this. So you can actually solve right for each of the vectors, and essentially you get this equation. You can solve this if say you just use 6 control points. Essentially you have a square matrix. The A matrix is a square matrix. So essentially you can just do a simple inverse of A to find A and B. So if in case you have a matrix which is not a square matrix, which is a rectangle matrix, so what do you do? Yeah, that's what is shown here. So you can use a normal equation, you can multiply by the transpose and take the inverse of this. So these equations, basically you'll use these equations to basically require A and B, to find A and B. Okay, this is okay, but what do you do if A transpose A is a singular matrix? So if A transpose A is a singular matrix, this inverse is not feasible, right? So you can use some simple tricks, like you need to add small identity value, the sigma times I. The sigma is very close to 0. It's non-zero, just close to 0, and identity matrix. That's called like, it's a trick actually used by a lot of people to find the inverse of the matrix which is singular. So I think MATLAB already does this in, if you use MATLAB for coding, MATLAB already does this for the inverse. And for C, you can just use that similar trick. Yeah, so basically using these equations, you can find A and B coefficients and use them to basically generate this image. Yeah, I did not explain the bilinear interpolation. So this is a final output image. Do you have any questions regarding spatial warping? Yeah. Exactly. So when I say non-integer positions, so when you map back the integer coordinates from the output image to the input image, they can be fractional values, right? They're non-integers. Oh, what I meant is, so if you, I think if you refer to lecture 5, professor talks about two types of coordinates. One is Cartesian coordinate, another is image plane coordinates. So image plane coordinates, essentially we consider is at the center of each pixel. So that's what I meant by fractional coordinates of the image plane. So in the Cartesian coordinates, basically starts from here, right? 0, 0, generally. But the image coordinates start from here. This is 0, 0, but the first pixel is at like 0, 0.5. So it's not like 0, 0 actually. We consider the center of the pixel. So that's why we call it fractional coordinates. So please refer lecture 5. He discusses this clearly. Any other questions? Yeah, you need to remember this transformation of coordinates from Cartesian to image. It's straightforward, but it's very useful. The diagonal control point, 2 points, they are not linearly mapped along they are mapped at exactly, right? So basically you need to find this point, you need to find this control point. Yeah, not manually. It depends on your figure actually. For this example, so I think for this problem we'll give you the hint that this lies on the center of this quarter circle. So from given this side of the image, you can easily find what this point is, right? Just circle equation. Yeah, I mean, first you need to find these coordinates, I mean, these control points, then you need to find which they map to in the original image, and then basically you need to find the... So input is essentially the coordinates of the output image. You find the A matrix using this equation. So essentially you get from where the pixel values are coming from the input image. So, but the pixel values are coming from non-integer locations sometimes. So for those non-integer locations, you need to do the bilinear interpolation or cubic interpolation to find the pixel value at the fractional integer point. Is it clear? For this example, I showed you a 6 because it's a second order polynomial. This is a contour, right? This is like a curvature of the circle. So you can't represent using any 3 points, I mean, using linear equations. So you need like at least 6 points or the second order polynomial. Oh yeah, so in this example, I am dividing the entire image into 4 triangles. For each triangle, 6 control points. You're right. So for your homework problem, I think you need to decide how many control points you need. So I think this is the easiest. You can see it's a simple transformation. Yeah, so this is looks like a rhombus. So basically you need to find some control points and then do the mapping and reconstruct the pixel values at non-integer locations. And this also. So the main idea is you need to find the control points. You need to explain like why you're choosing these control points and you need to decide what type of order of the polynomial warping you're using. So the hint for this problem was essentially if you have a curved contour in the image, you can use the second order polynomial. Any other questions? Okay. So this is some more hints. So one thing you need to remember is you need to also, when you map back the points, you should also find out if the point lies within the triangle or not. So sometimes to do this, essentially, it's very simple. So triangles, since you know the control points, you can basically consider the linear equation passing through those control points and try to figure out whether the points which you obtain map is on which side of the line. So if for this example, assume if this is a rhombus, this is a straight line. So you need to find out if the point lies on the right side of the within the image or outside the image. So this will be useful for, say, the boundary point. So just this one hint. And the main thing which we are looking for this problem is how you do the control point selection and what type of model you're using. And if you encounter any artifact in the transformation, you need to discuss. And I think you should also discuss whether you are doing forward mapping or reverse mapping. And yeah, and whatever you discuss, whatever you find in your output results actually. So that's for the first problem.
Just differentiate between, how to select, how to decide whether it's a forward or...
I think it depends on the problem. So for the given problems, I think most of the problems require reverse mapping. You can try forward mapping. Then you'll observe the problems with forward mapping. And you can use say, forward mapping, as I said, it can result in non-integer locations, right? You can still interpolate from the other pixels, but you'll see some artifact. So if you want to try forward mapping, you can do it, and you can also discuss the artifacts. But for this problem, I think for the first problem, what we expect is you need to generate these kind of warped images. Any other questions? Okay, then okay, I'll go to the problem 3. So problem 3 is also pretty straightforward because all the instructions are there in the homework assignment sheet itself, what you need to do. So as I explained, texture analysis and segmentation is actually a very practical problem. It arises in a lot of areas. So in this problem, we have 2 parts. One is to do the image clustering and another is to do the image segmentation. So image clustering basically tries to classify, given like several images, it tries to classify images of similar kind into one cluster. So for this example, for this problem, essentially texture 1, texture 4, texture 6 belongs to one cluster because they're pretty similar, right? Similar in texture. So your job is to actually use texture analysis. You need to do some kind of texture analysis using loss filters to basically do the clustering of the images. So you use loss filters to generate feature vectors, and you use some classification algorithms like k-means to do the clustering. So that's for problem A. Problem B is also very similar to problem A. Instead of doing the clustering, you're doing a segmentation. So let me give you some hints for the problem 3. I think Professor has not covered that in the homework, right? In the class. So I don't know whether you need some hints for that, or I can go to the sample problems. Okay, let me go to sample problems. Okay, let me explain k-means algorithm. I don't know if Professor Ko will cover this, but just a brief idea on what the k-means algorithm is. So k-means algorithm essentially, so given set of points, you want to cluster the points which are similar to each other. When I say similar in some sense. So for example, if you have the points represents the features, so you want to classify features which are close to each other. When I say close, it means in some space. So if you have some feature vectors, say in the Euclidean space, you basically consider the distance as a metric to find out if two features are close to each other or not. So if the Euclidean distance is small, then it means that the features are close to each other. Excuse me. So this is a algorithm. It can be like supervised or unsupervised algorithm, which can do the clustering automatically. So so the input for this algorithm is essentially the features, the data points, which here is the features. So features are like n-dimensional features. So essentially you're given n-dimensional, say, some m features or k features. You want to cluster them into some classes. Say, okay, when I say k means, it means like k classes. So the idea is pretty simple. So you assume there are some k centroids, and basically you want to measure the Euclidean distance of the features with respect to these centroids. And if they are close to a particular centroid, you assign the class label of that centroid to the feature, and you recalculate the centroid points. That is the centroid location, or the center or the mean of that cluster is recalculated, and you repeat this iteratively. That's actually the main idea of k-means. So this is actually the procedure of how the k-means is done. I'll go through this. This is useful for the problem B actually, and you use the same clustering algorithm for problem A as well. I mean the problem 3A. So at the beginning you initialize some cluster centroids. Assume that you have 5 clusters. So you choose like 5 centroid points either randomly or based on the data points itself, based on your image feature, the features. And then, okay, this is specifically for the texture for the problem 3B. So what you'll be doing is you'll be finding out a feature vector for either each pixel or the entire image. So for the problem A, texture classification clustering problem, you'll be constructing one feature vector for the entire image. But for problem B, you'll be constructing feature vector for each pixel in the image. So because this you're doing because in the problem A, you know that the entire image belongs to one type of texture, right? This is the entire thing is one texture. On the other hand, you're not sure of the entire image because you already told this is a mixture of different textures, right? So you're trying to find the label for each of the pixel points in the image. So that's why if, in this, when you're applying this k-means algorithm, so essentially you'll be constructing feature vector for each pixel for the part B. So here this example is for part B. So you obtain a feature vector for each pixel point. The feature vector here is obtained using something called as loss filters. I think Prof will cover this week, and the next discussion will go into more details on the filters. So you'll be calculating the feature vectors for each of the pixel points in the image. Then you obtain a label for each of the feature vector. That is, you find the feature vector which is, you find the centroid which is closest to the given feature vector and assign that label to the feature vector. And then you recalculate the centroid. So essentially you will be, in the first iteration, basically you're assigning labels to all the feature vectors present in the image. And then you're recalculating the cluster centers. That is, given these clusters and the feature vectors for each of the cluster, you basically recalculate the centers of the cluster using this equation. And this is nothing but just taking a mean of all the feature points, all the feature vectors present in that cluster. So just taking the mean, so just the average. And then essentially you reiterate these steps till it converges. So converges in the sense the cluster points don't change, the cluster centers don't change. So till that point you basically run this algorithm, and after convergence basically you have the image which has different labels, that is different pixels have different labels in the image. So in this example then you basically convert this labels to the grayscale values. So this is an example of the k-means algorithm. I don't know if I have more time. Operator, how much time do I have?
1 minute.
Okay, not much time left. Okay, I think then that's all for today. If you have any questions, you can ask me now.
Zoom exam.
Right, that we'll talk to Professor and confirm. Yeah.
This concludes EE 569 discussion on Tuesday, October 15th, 2013.